everybody. My name is Vishakha. I work with Professor Roy Yates on this topic of using age of information models to enable low latency services. The kind of applications that we're interested in includes vehicle to everything, augmented reality, and typically in these applications, you have a source that sends some form of an update. So in this case, it's a car that sends a device status, say location, to the network for processing. The network receives these updates, does some form of a computation, and sends it to a monitor. And typically these applications, they require a certain response time. So for example, in the case of V2X and mission critical IoT systems, the required response time is around 1 millisecond. For AR, VR, and tactile feedback kind of applications, the response time is around, the required response time is around 1 to 10 milliseconds. And this actually corresponds to some physical phenomena. So for example, in the V2X application, an update that is delivered every millisecond corresponds to a car that moves every centimeter. And for the AR, VR applications, if a user moves and the rendered image takes, say, more than 10 milliseconds, it can cause motion sickness or even discomfort as well. So the question is, does the current network architecture support these applications? So we consider this cyber-physical system application. We have a master control on the left-hand side, and it does it sends a movement update. It takes around 250 microseconds, and that update travels through the network, and it is received by slave robot. The robotic device processing takes around 250 microseconds. For this application, the end-to-end latency requirement is 1 millisecond. So the leeway for the network is around 500 microseconds. And so an update cannot afford to spend, say, more than 100 microseconds on a node. So where is the delay? We want to answer that. Is it the propagation delay? We say that the propagation delay is almost negligible. The Cosmos testbed recently employed 100 Gbps, 200 Gbps links. So we contend that the bottleneck is actually in the packet handling. It's the input-output processing that is limiting the future performance. And typically in a router, an application, this is the application that typically runs in a router. You have packets that are received on the NIC, and it's received by the receive core. The receive core or the receive process does some sort of a processing using the shared memory structure, and then sends these packets to the transmit core to send it out. Now, there is a critical success factor in these applications. It's the synchronization between multiple processes that are accessing the shared memory. And we would like to study this aspect. So we take this simple application, try to model it using this abstract model, where you have a source that sends its update to the writer tries to write to the shared memory, and then you can imagine that there is a client that requests the reader to read from the memory so that it can do further stuff. And because you have reader and writer that are accessing the shared memory, you would have to use synchronization primitives, and those are the way to avoid race conditions and ensure data correctness. Now, synchronization primitives have been a topic of study in computer science for many years now, but here we would like to understand the impact of these primitives on the timeliness of information that is stored in the memory. And the performance metric that we would use is the age of most recently published update. To summarize what age of information is, it's a process as a function of time. The age increases in the absence of any update. At some point, an update arrives at the server that is represented by an upward triangle. The server starts processing that update, and after some time, it delivers that update that's represented by the inverted triangle. At this instant, the age at the monitor is reset to the value equal to the elapsed time since the update was generated. We also talked about synchronization primitives. Here we are interested in evaluating one synchronization primitive, which is readers write a log. So if you have a reader that is reading from the memory, it puts a read log, and if a writer comes in, its request is denied. Next, If the writer is writing, puts a write log, and if the reader comes in, its request is denied. So in summary, readers write a log, it actually enforces mutual exclusion between the readers and writers. A logless alternative of RWL is what is called as read copy update, RCU. You have a reader if it's reading a value of a data item. The writer, when it obtains the newer value of the data item, it can start writing. So RCU is actually a lockless concurrency construct. In summary, it actually allows concurrent forward progress for both readers and writers. I motivated this application of understanding, okay, how the shared memory is actually a bottleneck. To reinforce this fact, I'm going to consider this timely mobile routing scenario where you have an application server that's trying to send something to a mobile user. So it generates an app update. The app update arrives at the router. The router looks up the forwarding table and forwards the app update accordingly. Now the user moves, it sends its newer location update, and this newer location update is updated in the forwarding table. Now, when the application server sends an app update again, it's addressed appropriately. But so we have this coupled edge processes over here. We have location updates that are sent from mobile terminals that will be written to the forwarding table. And then there will be app server updates that initiate the request to the reader process in the router so that they can be addressed properly. So we can see that there is a contention to access fib here. But what could go wrong in such systems? So suppose an application server sends an update. However, that app update is misaddressed because it read a stale address. So this results in increased age at mobile. It's this phenomena that we would like to study both analytically and experimentally. So my work kind of tries to compare RCU and RWL as shared memory synchronization primitives for fib access, and I focus on developing analytical models, especially using stochastic hybrid systems, and even do some sort of experimental evaluation on Cosmos testbed using this high packet processing framework called as TPTK. To focus the first part on the analytical study, we are interested in basically two aspects. One is that the freshness of app update at mobile, it depends on what kind of synchronization primitive you're using for fib. And it also influences if the app update is addressed correctly. And there are certain design choices on how you would process an update at the router. So suppose you have two updates that are queued at the router, they're waiting to be addressed. So don't serve the stale update, just serve the freshest one. And you can model this scenario using preemption, and the router can actually preempt the update that is currently serving when a newer update arrives. So I would like to also kind of present some of the results. The first analytical study on the synchronization primitives. Here you can see I'm plotting average age at mobile user as a function of user mobility rate. Clearly, as the user mobility rate increases, the average age at mobile user also increases, because with increased mobility, the app updates are going to be frequently misaddressed. The upper curve, which is the red curve, which represents when RWL was used as a synchronization primitive, and the blue curve represents when RCU was used as a synchronization primitive. Now, RWL reads are usually slower, and in this case, I'm setting RWL reads to be 10 times slower than RCU. And because of this, in the case of RWL, the app updates would be delayed at the forwarder because the reads are slow. And therefore, you see that the age performance for RWL is not that good. Mm-hmm. However, a surprising result that we found was when the read times for both RWL and RCU are similar. In this case, we see that RWL performs better age-wise than RCU. It's because at higher mobility rates, the fib is likely to be outdated, but the mutual exclusion principle of RWL, because RWL is kind of enforcing the reader to not read while the writer is writing, it bars the reader to read the stale update. And the app update is less likely to be misaddressed. and therefore you have a better edge performance for RWL when the read times are actually similar. So this is a part of the analytical study I presented. The next, we also did some experimental study on Cosmos testbed. So we took our update forwarding scenario, tried to implement it and evaluate it using on the Cosmos bed. So the application server and the users, they are now emulated on a source machine. And then I've also implemented forwarder on a different machine. And with this, we would like to understand the effects of concurrency constructs and also evaluate the impact of input queuing, that is actually like the high packet processing framework, they use some sort of a batch admission procedure to obtain high throughput. So, well, here are some of the studies that we conducted. One thing that we noticed is that DPDK or any high packet processing framework, it's optimized for maximum packet throughput. So they use some sort of a transmit API where it kind of sends a burst of output packets onto the transmit queue of an Ethernet device. And the question that we would like to ask is that DPDK or even other high packet processing frameworks, do they support timely delivery of information? To answer that and to study that, we conducted a baseline experiment where we bypass the forwarder lookup. It's now just the source machine, and the source machine sends the packets, and the receive thread in the forwarder receives the packets and sends it back. What we observed that for a low enough sending rate, as you increase the sending rate, the average age reduces. This is conventional AOI behavior because frequent updating would reduce the age. But however, after a certain sending rate, we observe that the average age kind of continues to increase. The question is why. So we studied this in more detail and noticed that for DPDK, we obtained that the average packets per batch for a low enough sending rate was around 1. As you increase sending rate, of course, the packet, because it's like a batch admission procedure from the DPDK side, the average packets continue to increase. And because of this, it induces queuing delay at the source machine, and therefore you obtain the increased average age at the multi-user. So with these, and so the question is, yes, DPDK and other high packet processing frameworks, they do not actually support timely delivery of information. So there are certain conclusions that can be drawn, and there are many lessons that can be learned. So for example, for software engineers, they should be careful in choosing synchronization parameter. They should understand their application requirement, the degree of contention that their application is actually going to offer. And for network engineers, you should know what is making your system slow and if it's suitable for timeliness. And if given a chance, you should also optimize the packet processing framework for timely updating systems. And for researchers like many of us here, there is a lot of work to be done. From these simple studies, what I observed, there was combinatorial explosion of system models and how you can design your systems. And you can also explore this notion of timeliness in other applications that deploy shared memory. So that's all.
Thank you, Vishakha.
Hi.
Very nice talk. I'm curious, what kind of switch or router you used, and what level of programmability you had? So you could change all the, you could introduce all these changes.
This one?
Yeah. What router you use?
This is just a baseline image, and I used DPDK to implement the router functionality.
Okay, this is already there.
Yeah.
Okay. Any other questions? All right. Thank you, Vishakha.